Yeah, this is my first time in Stockholm AI, actually, so I'm glad to be here finally. How many went to the... can you hear me? How many went to the machine learning meetup like 2 weeks ago? Ah, it's a big overlap. Cool. And I'd like to just briefly share some lessons learned from some work we have been doing at Peltarion in the last couple of weeks, months perhaps, with respect to this automated hyperparameter tuning. And I was actually inspired by this from KDD this year in August. So Google visualized or demonstrated their Google Vizier service. And I'll talk a little bit more about that and just a bit about the background for me and Peltarion and some other stuff. But then I like to do this kind of inverse agenda, so I'll actually do a demo very quickly, and then later do the introduction. So this is a bit weird, but I think actually that's rather useful to do. And just to give a very brief background about myself as well, I've been working with AI for a really long time. Is it anyone here that remembers Buyer's Guide? No? Ah, awesome. Still one person. I'm not that old, but I'm rather old still. Anyway, that's really the reason I got started with machine learning and AI. So that was basically the first automated shopping site. So before Price Runner and these kind of sites. So it extracted a lot of information from different websites and basically helped you to find the best place to buy a certain product. And that became really cumbersome to maintain and to program manually, so you want to automate that somehow. And that's what you use basically machine learning for, trying to automate the programming of an intelligent behavior without having to manually enter rules and code. That's in a nutshell what machine learning is about. But then continue in academia for some time and quickly went back to industry. And in recent years, I've been at Spotify for like 4 years, heading up a research group that basically makes use of big data and machine learning techniques to understand user behavior. And since the beginning of this year, I've been at Peltarion, where we work with democratization and industrialization of AI. So that basically means trying to help other companies getting started to use the state-of-the-art AI techniques. And by the way, please ask questions. I think it's much more fun to have like an interactive discussion. Otherwise, I just keep talking on and on and on and on. Peltarion, just to give a very brief background about that, that's a company that's actually been around for like 10 years, but just with the two founders. They worked with a number of interesting companies like NASA and Tesla and Intel in the past. And recently they have received this big funding, so we're rapidly expanding our efforts in trying to help companies get started with the latest and greatest techniques. So these founders have been working with the techniques behind deep learning for a really long time, even before it really became popular and broke through. And this is from KDD this year. I'm sitting in the audience here, and these are some people from Google, and I'm starting to talk about this technique for black box optimization. And it was, everyone was super excited to hear them speak about this. I was actually very frustrated, and I tell you shortly why. But it was really interesting to see, how important they feel this is. Basically, nothing they do when it comes to any deep learning model is without trying to do some automated hyperparameter search. So it's just essential, and it became really clear when they spoke about this, how important it is to be able to do this if you want to do serious machine learning, I would say. And what it's really about, it can be boiled down to this really short piece of pseudocode. So you can talk about some study you're doing. That can be, you have a sort of model, and you have a set of data sets that you want to train on, and you have a set of hyperparameters. So that's basically a study, and then you run a number of experiments on it, and you have some kind of algorithm that gives suggestions for what values these hyperparameters should be. And you run the trial, you get some kind of objective metric out of it, and you feed that back into the algorithm, and you get a new suggestion for new values to try out. And you just do this in scale, in parallel, hopefully. So far really clear, right? So no questions so far, I guess. And this is really the functionality that they have in the Vizier API. So they have a set of workers which can run like 100 machines with different parameter values. And they have some kind of database that stores the results and the values for each of these experiments. They have some kind of functionality to automatically stop experiments that is not going that well. And to find basically these dangling workers that seems to be stuck for some reason. And then also, of course, some kind of suggestion service that suggests new values to experiment with, and you want to do this in an as intelligent way as possible. So they also went through a number of design goals for how they designed Vizier. And ease of use is, of course, very important since they have so many different people that are going to use this inside Google. So they have some tooling around it, some web front and you can use, even some notebook environment you can use, and also a set of different language bindings. But mainly, of course, it's Python that you're making use of and TensorFlow. It's also a number of other important features for this. Being able to monitor and just introspect the process as it's happening is super important because it's so easy to have some set of values that doesn't really work and just make the complete experiment fail. So to be able to detect that early on is very important. And yeah, they had this extreme scale. I guess no other company is doing it at the scale that Google is doing, but they can even have, for a single study, millions of experiments going on. And that's a lot. And number of studies, I didn't really mention that, but I can imagine at least tens of thousands of studies being performed all the time. And one of the things they have, which I haven't heard anyone else have before, is that they also have an automated algorithm selection. So you have to have some algorithm that tries to optimize the parameter values. So this is not a learning algorithm or the optimizer in the model. I'm talking about the algorithm outside of the experiment that tries to come up with the next suggestion of parameter values. So for that, they have a number of, I think, 8 different functions that they can choose between. They have a default one, which is this Gaussian process version of it, but it can also automatically switch during the study to other algorithms to choose from. So that's really a neat kind of.
So why did why would you feedback? Why wouldn't you feedback the first trial back to the algorithm itself and rerun that? Because in the client,
Yeah.
you had to first trial and get the next hyperparameters, and then call the client to actually use it. So
You do that. Yeah, so normally they start with a single algorithm, like the Gaussian process bandit version, and they. Oh yeah, okay. I see. So the question is basically why don't they basically feed it back to the client? Yeah, directly. So they do that. They start with a single algorithm. They run that for a time, but then they can recognize that this algorithm is not really finding an optimal version. Perhaps it's completely random in the way it's selecting values, and it doesn't see an improvement in the results for the objective function. So then they can switch over to some other algorithm that seems to be working better for that type of model or that type of data. But I would question that. I try to get them to give some kind of statistics on how often it actually switch, and that actually improves the functionality, but they couldn't really give any such statistics. I think this is more like a cool feature to have, but not really that useful. That's my guess of it. So one additional, besides what I mentioned, is also the transfer learning aspect. So what you quickly realize, and this is a functionality we don't have at Peltarion yet, is you rerun a lot of experiments often. And for the most existing solutions, you have to basically start from scratch every time. You can't really learn from the previous experiments. So previous studies that has been run, you basically throw that away and start from scratch every time. And that's really wasteful. But it's also very hard to copy, perhaps it's a different set of parameters you have, the second study. So how do you copy that? And it could even be different, data you have, different normalization, different, whatever. So it's very hard to just copy that, knowledge and insights from previous studies back into new studies. But they have a rather smart version of that that apparently, according to them, works very well. And that was like a big improvement in the performance for their system. I said I was frustrated at Google, and this is the reason. They probably spent like half the time during the presentation talking about this cookie project. And they actually tried this Vizier functionality for a lot of different type of problems, not only machine learning, but also for real, like baking cookies experiments. So they literally had some cook, they had a recipe, and they had people trying out the cookies. They were, evaluating how well the cookies were tasting, feeding that back into the Vizier algorithm, and it proposed new changes to the recipe. They baked the cookie again and just continued to iterate to find the optimal cookie. And for some reason they were really proud about this, and they could find a new recipe that's never been seen before, and some kind of chocolate cookie that Vizier came up with. So.
One question regarding the slide before.
Yes.
How did they do the transfer?
Oh yeah. So in short, I've tried to write a very brief description of it, but for every study, they usually use Gaussian processes to try to come up with a posterior distribution of what the parameter value should be, and in the end, you have basically some kind of multimodal distribution over the values of each parameter. But then when you have a set of studies, you can basically stack these previous Gaussian processes on top of each other. And I assume basically weighting them in a like exponential moving average style, you can have an ensemble of Gaussian processes. So you get some kind of new distribution over the parameter values that is based on a set of different studies from the past in that way. So that is the very brief description that they mentioned. But that only works if all the previous studies was using the same type of algorithm, which is Gaussian processes. And I think basically that's the only thing they more or less make use of. But I think you can do other stuff, actually. So, okay, that was basically a very quick introduction to why we became a bit interested in really spending time with doing this ourselves. So I'm going to demo now very quickly one project that is using this right now at Peltarion, and this is the project of Deep Weather. How many of you have seen this before, Deep Weather project? Okay, like half of you, so I do it very quickly. This is a very cool project. One of the things that I became the most fascinated with when hearing about what Peltarion has been doing in the past, but basically they're forecasting weather. And they do that for a very specific use case, which is trying to predict the wind turbine energy production. And by doing so, basically energy companies today need to do that for like 12 hours in advance, for 24, up to 48 hours in advance. They need to make a prediction saying how much energy production each turbine will make. And every error that you have in that prediction will result in some cost. And that cost accumulates to like 4 billion Swedish crowns per year. So if we can improve that accuracy, that can result in significant savings for the energy company. And the current solution is using these kind of supercomputers that simulate the physical worlds, and the SMHI and the European Weather Center, and how they today have these kind of more physical representation of the world and simulate each step forward to make some kind of forecast. And they're really slow, they're inaccurate, and very expensive to make these kind of predictions. So can we use AI for that instead? So they try to basically take an AI model and throw in a set of different data sources, such as satellite imagery. We have data from weather station around the country and in Europe, data from wind parks and more. And we throw that into a model looking something like this. where you can feed in the data from the left, it learns some kind of representation of it, and in the far right you get some kind of output saying this is the energy production for a certain wind turbine. And this is a visualization of the weather forecasting. So the top row is a 48-hour prediction for different aspects of the weather, such as temperature, pressure, and wind direction. And in the bottom row, you see the ground truth of what the weather actually turned out to be. And it actually is surprisingly accurate in this one. With that, I very quickly switch to the demo, because I think that's the most interesting thing. Not really sure. I haven't really prepared this that well, so please forgive that. But here is a TMUX session running on one of our servers. It's actually running an experiment right now here with some metrics in it, but I thought I could perhaps start another one. And let me show you some other code. I guess most of you are used to programming, so you understand the code when seeing this, right? This is basically all you have to do right now in our library to start up a automated parameter search. So this is defining the parameter space. And you can recognize some parameters such as number of hidden units, dropout, what optimizer to use, and so forth. And we use a tool or a library called Hyperopt, and it has some predefined distributions you can assign to each of these variables to begin with. And one of them can simply be some kind of uniform distribution for the hidden size that basically goes from 500 up to 2,000 hidden units. Or it can be some kind of log uniform distribution for dropout, which will have much more values in the lower section of this range compared to the upper section. And what they can also do, which is really nice with Hyperopt, is you can have a tree of these parameters. You actually don't see that well here, but for example, this is a complete discrete choice. So it's choosing either to use the RMS prop or the Atom or Atom Max optimizer. And it's not really a continuous space for these variables. And that's one of the strengths of this specific library. But what you can also do, imagine if we, for example, had the number of layers as a parameter, then the number of hidden units become dependent on that one. If you have one layer, you may have X number of hidden units in first and another set of hidden units in a second. So we need to have a conditioned set of parameters depending on the value that the optimizer is giving to it. So that becomes really complicated. And what you can do with this is basically build up an arbitrary tree structure where you say, depending on the value of 1, we have these set of parameters. Depending on some value of those, you can have a third level of different parameters to work with. So that's one of the core strengths of this library. And also, I hope you see that this is supposed to be a really concise and easy to understand piece of code to just define the space. Just work through this space of different parameter values and tell me what the best one was. Yes? Very rough. I mean, if you can't learn anything, if you can't get the model to overfit at all, for example, I mean, that's one of the first things I try to make sure you can overfit. If you can't do that, then you probably need to work a bit more with how the model works and how you represent the data. But as soon as you see that, so you understand it can actually learn to find some patterns at least, you can start to run some automated tuning. Then you know it can learn something. It's just need to find the optimal, regularization parameters and whatever. But good question. Yes? Yes, very much so. Yeah, I mean, I can, without saying too much, but a very big change. If I can give some detail, I think we were up to 0.5 in a certain metric. We came down to 0.4 Then we actually went back up because we found some bug that we needed to fix. But we can move up and down rather quickly with a single study, at least 20-30% of the metric, I would say, if that gives some kind of insight. But the thing is really interesting, just to share one other learning that we got from one of the models, it was more of an LSTM model, and we thought, it needs to have at least some number of layers of these LSTMs to be able to learn some more abstract representation. But it turned out just having one layer, but the really wide layer, was really the absolute best representation to have. Well, you can have many of these LSTMs in sequence as well. So that's one learning that you can see from this. That is not always very intuitive, at least. Cool. So what you do, you can choose whatever settings of these parameters you want, and then you can start an experiment. So let me show you how to do that. So I started one just before coming here, and it's been running 5 experiments or trials, as I call it here.
Yeah, just a follow-up question. Okay, so how big space can you give it? It sounds like you can give it infinite big and it should still optimize quickly.
Yeah, you shouldn't. I mean, one of the things the Google people said as well was you're sometimes surprised how well random search works. You know that grid search is very hard to do in these kind of spaces. Just imagine having like 5 parameters, each of them taking like 10 different values. You have 10 to the power of 5, 100,000 different combinations just to work through the space one time. That's impossible. So grid search in that kind of space doesn't work. If you do random search, at least you are likely to more quickly at least find and work through the space. And there are a number of actually informed random searches you can do, these quasi-random things that actually makes them even better. But with this one, it should be a significant improvements to random search. So then it's hard to give like a absolute value how big the space can be, but you can easily say it's significantly much bigger than you can with a grid search. And it's also significantly bigger than a random search, I would say. So that at least this is one conclusion you can make. So just having these 5 parameters would be impossible to do in a grid search way. Okay, so hopefully now we'll interrupt one of these runs. Now perhaps Lars will be angry because I will be stealing some GPUs on this machine, but I don't care. So this is the Power LSTM model of the weather project. I will give it a new name. So, I mean, you don't need to understand all the parameters here, but it's kind of simple. And this top session will simply start like a master process, the one that suggests parameter values for other workers to have. So I can simply start that one. And now I need to start some workers. So I take one worker, and that allocates one of the GPUs. This machine has 4 Titan X GPUs in it. So I choose GPU 1. I need to say fetch parameter values for this new experiment with number 4. And now the worker started. It actually went up, asked the master process for a new set of parameters. It got some values back, and now it's starting an experiment. And this will take like 20 minutes to run. And while that's running, we can also start another worker if we want to. And in this way, we have 2 workers working in parallel, trying to start exploring this space. Hopefully that gave some insight into the how you operate these kind of systems, and this can run on many machines. You have basically a Mongo database underneath where the results is being stored, and they communicate over the network to talk to this master process.
And they also feed back the results.
Yeah. So as soon as they are finished, they report back up to the master process, saying what the objective value was. And right now it doesn't have any, so loss says the best losses so far is infinite. That's not a good loss value to have, but as soon as one experiment completes successfully, it will have some more insights. But actually this Hyperopt will start with just doing random search for the first 20 experiments. So before it actually have seen enough experiments completed, it can't really make an informed decision on the next set of values. So the first 20, you can tune this as well, of course, but the first 20 will still be random search. And then the Hyperopt starts to kick in. Yes? Yeah, it will use a very cool algorithm that I will show very shortly.
It looks like your first process
Yeah.
restarted.
Yeah. So then probably it got some, batch size is one of the parameters here. And if you choose too big a batch size, it won't fit in the GPU and it will just crash. So that will mean it will basically ask for a new set of values, and hopefully with a random search in the beginning, it will get a better value for the batch size. And yeah, that's one issue that we should really try to fix in a better way. And the reason for that is rather interesting, because we also seen that having a large batch size is really important and seems to correlate very much to the objective value. So as soon as the algorithm kicks in and stops doing random search, it will start to zoom in very quickly on high batch sizes. And that will cause, basically after a while, every process to fail, because it will always choose too big batch sizes. So then it will continue like 4 times in a row, then just gives up. And we've seen that a number of times when you start to see this correlation between batch size or sequence length or number of hidden units or something else that increase the GPU usage, that it very often zooms in on that and the whole process just stops. So that's an issue we should try to solve. Yeah. Yeah. I will talk about that very shortly. So we have early stopping that will hopefully stop it much sooner than 200 epochs. But great question. Okay, back to the presentation. How much time do I have left, by the way? Is it? I wish so. I speak too much anyway, so. Okay, so the plan now, I'm going to talk a bit more about the introduction. Oh, I forgot one thing, sorry. I'm going to show you one more demo thing. So what happens, when you run a number of experiments, you want to analyze that somehow. And one way is simply to use TensorBoard, for example. Let me see if I can. Oh, right. Oh, on this resolution it will be horrible, but oof. The okay, this perhaps is okay. Here is just a very small study. It haven't even reached the 20 number of experiments necessary to start the actual intelligent selection. But here you can see each experiment is a single line, so to speak, and this is the validation metric that we're looking at. So this is what we are optimizing for. So we're training it, we have some train metrics, we have some test and validation metrics, and we basically want to have as low value as possible for this one. But what you will also see regarding your question is that some of these are much shorter than the others. So this one is super short, another one is much longer. So this one perhaps ran for 150 epochs, this one perhaps for 10 or 20. And when you can basically use, I'm not sure if you've seen this reduce learning rate on plateau kind of logic that Keras has and some other libraries as well. Yeah. Yeah. Yes. Yeah. It is cool, right? And then you want to see, what is the difference between the green one and the yellow one, for example. But that you can basically use the tooltip. I don't think it will work here, but you can actually see if you squint your eyes, perhaps, the values for each specific run here. But it's not a very good tool to use TensorBoard to analyze the results in a good way. So we have some notebooks as well that can give some more insights into how the experiment worked. So let me see if I can connect to that one. And if we can reconnect to the kernel, perhaps. And in this one, I can basically fetch the results from this Mongo database that have experiments. This is an old study with 182 experiments in it. It had set of parameters and had 55 incomplete or failed experiments and 127 succeeded. And then we can try to visualize this way in some kind of table. So these are all the experiments per row, and it's sorted on the test metric. So that's really the objective value that we have, that we optimize for. So the top one here have a certain set of these parameter values that gave, in this study, the best result. And then we have all the rest, and you can see how they increase. In the worst test metric was 0.83. And in this way, it gives a first very much improved overview of the results compared to tensor boards visualization. And here you can simply, if you are the simplest action to take is simply to take the top row here, add that as values and go for that. That should be the best values that we've seen in this study. But you can do more. Perhaps you want to get some understanding of how important each of the parameters are. And this is simply doing a Pearson correlation between each parameter and the test metric. And if you look at the bottom row is basically showing the correlation between the test metric and each of the parameter values. And one of them here is really high. It's 0.6. So the weight decay seems really important to obtain a low test metric in this case, because we want to have a low one. So basically, since it's a positive correlation, it means low weight decay will have a low test metric. The sequence length was rather important, but the dropout didn't matter at all. The learning rate wasn't that important either. So these seems to be the two main parameter values to make sure to get right in this case. Yes. Yeah, I would say so. Usually, I've rarely seen more than 2 being important.
Can you play around data augmentation, optimizer?
Sorry, what do you mean?
Data augmentation, like change the shape of the image or the color.
Yeah.
The weight, the angle. The model works.
Yeah, so the question is if you could change the data to do that. And as long as you can formulate the data transformation as a parameter that the optimizer of the Hyperopt optimizer can actually feed into the experiment, then yes. Then you can, if it's some kind of preprocessing or some normalization change or how you initialize the variables or whatever it is, as long as you can formulate it as a parameter that can be fed into this parameter space that you saw in the beginning, then it can be tuned in this way. No, we've just worked with this for like a month or something. But I would never enter a Kaggle competition again without using Sure. That's clear learning. I would be helpless to not, having started to use this, you realize you can never live without it anymore. That's... No, it's an open source library. Yes. And then if you see some kind of, the weight decay, for example, seems to be really correlated, we can do some scatter plot like this to just see each dot here is basically an experiment. And then you see the test metric, and you see this really clear linear correlation between the weight decay and the test metric. And you want to have a low test metric. So these are good experiments with a low value of 10 to the power of minus 5, I guess in that case. No, to 7. Cool. Okay, back to the presentation. It is positive, but it's because you both want a low test result and a low weight decay. So they both are going in that direction, and that's why it's positive and not negative. No, it's not the importance you see here. It's still super important, but you want to have a low value, and it's important that you have a low value of the weight decay. So if you have a high value, that's really bad. So it's really important, and it should be low. That's basically the conclusion from this. And you can do other stuff like sequence length. This one doesn't seem to have a strong correlation, for example.
Can you do heat maps of 2 variables?
Yeah, we actually have that. It's partly what this one is showing. This is more or less a heat map of the different parameters. We tried other visualizations as well, but this one is very, I think, rather intuitive to look at. Okay. So now back to the introduction then, to the last part of the presentation, perhaps. Whoops. What happened here? So what we want to do, basically, this problem of the combinatorial explosion of hyperparameter values that we get when working, especially in this deep learning session. But remember, this is not just for deep learning. It's not just for machine learning. You can even use this for bake cookies, for example, or how to tune the coffee machine settings at work or whatever. It's a black box optimization technique, and the black box refers to can be anything. I actually think that's a negative thing, but I'll get back to that later. And we have a number of standard techniques. The simplest one is a grid search, but as said before, if you have 5 parameters, 10 values for each, it's 100,000 values to cover. You can't run 100,000 experiments, so it basically fails very quickly if you have a number of parameters to tune. Random search is better and surprisingly good. Hand tuning, people think is really good if you have experience, but usually, even with years of experience, I would say you usually have the wrong intuition. So at least, perhaps it's just me, I don't know. Otherwise, the most common by far is using Gaussian processes for this. So they basically you basically apply some prior for each parameter. You get the results from each experiment, and you update this distribution and get some posterior, and that you basically sample from that and get some new values out. How many of you know what Gaussian processes is or have seen? Okay, I don't need to explain that then. But what Hyperopt is using is another algorithm called a tree structure parson estimator. And I'll give a quick intro to what that really is. And it's supposed to, according to themselves, to be better than Gaussian processes. I'm not sure Google agrees, because they are not using this. And it's hard to really give an objective value, but it solves at least some problems that Gaussian processes have. Oh yeah, this is a short overview of different open source tools that do exist today. And here is the Hyperopt version that we're using. We added some functionality to it though, but probably one of the other most interesting one is Spearmint. This is the other one I really considered, should we use this one instead of Hyperopt? But I went with Hyperopt in the end. Spearmint and basically all of these others are using Gaussian processes as the algorithm. It's nice with Spearmint. It also have this centralized MongoDB support, so you can run it in parallel. Many of the others don't. And there are so many names for this kind of optimization. So this beige opt, when you first read it, says, oh, it supports all these 3 different things. Actually, it means exactly the same thing, just different names for it. And that's the usual case in research. Also, SMAC, it's basically exactly the same thing as all these 3 things. It's just people are giving it different names. Vecca is also very popular in a Java and GUI-based tool. This one is perhaps a bit different than some of the others. It doesn't only tune the hyperparameters. It can actually switch out the whole model and say, I want to run some support vector machine and random forest and some deep learning networks and something else. And it can actually select the model in a bit more informed way. So that's kind of interesting difference with that one. but it's Java, and who wants to use Java? Not me. Okay, so back to the tree structured. I hope I didn't offend anyone here by saying that. Back to the tree structured parser estimator. And this is just an outline, an overview of the different steps of that algorithm. So it basically starts by taking these experiments you've seen in the past. It needs to have at least like 20 of them before it can be used. But then sort these trial first on the objective, like validation accuracy or the test metric. Then it actually splits these experiments in the top 20%. It's also a tunable parameter, but usually like 20% is put in like a different group, saying these are the top experiments that we have. Then another difference is it basically tries to model the likelihood of the parameter values for each of these groups. So you basically feed or trying to fit a GMM, a Gaussian mixture model, to each of these groups. So you assign some kind of distribution for each of the parameters. You stack each of them for each of the experiments, and you normalize it, and you get this kind of mixture model basically of each of these two groups, the top one and the rest. And then you basically sample some number of values from the top group. That could be some new values to assign to the next experiment. And then you want to sort them somehow. So let's say you sample 100 different values. Then you want to rank them somehow. So then you take this ratio. So you basically divide the value you get from the likelihood of the top group with the likelihood of the bottom group. So the bigger likelihood that the values have for being in the top group, the top 20% performing experiments, the higher ranking it gets. Yeah, and a lot of people is just, what is he talking about? But I'll share a bit more. This is just an overview of how the whole algorithm works. So the first step was basically trying to split it into 20% group. So here is like a set of experiments, some kind of test metrics that you want to have as low as possible. So you just find some kind of threshold saying these are the top experiments and the rest is the rest. So the first thing to do. And then you want to build this kind of likelihood distribution for the top group and the rest group, so to speak. And what this really means is imagine a single parameter right now, like weight decay. And imagine in this case we have 5 experiments. So one had the value here, one here, and I think it's 2 values here. And you basically assigned some kind of Gaussian around each of them and sum them up. And that becomes some kind of multimodal distribution. That basically is the likelihood distribution that you have for the top group, for example. And then you just normalize this to make it a probability distribution. So it's basically, I mean, it's 1 Gaussian per experiment. So in this case, it's like 5 experiments. Here you have 1 more experiment, and it becomes slightly different. I wish no one asked that question. Actually, this is really, I mean, the reason that it's called a Parson estimator is that, have you heard about Parson before? Yeah, perhaps some. But if you know k-means, for example, that basically says, give me the neighbors that are the top 3 closest to a certain point. So you set a fixed number of points to be in a certain space. You can do a similar k-means, but saying a Parson nearest neighbor. And that's basically saying, give me a radius around this point and include all the points in that, no matter how many they are. So instead of having a fixed number of points, as k-means has, you have a fixed radius to the similarity. So that's basically what they're doing here. The fixed version here is the standard deviation. So you can basically, the simplest version is simply say, I assume a 0.1 standard deviation and use that as a Gaussian for each of the experiment. Hyperopt doesn't actually do that. And they say they have a magic formula in the code. And I've been digging into the code of Hyperopt, and you can tell it's been written by mathematicians because it's impossible to follow. And the parameter names is some kind of letters, and you can really never understand what they mean. But they have some kind of heuristic. They simply call it in the code hidden or magical formula. And then they get some kind of standard deviation that is not as simple as this. So it seems to use the prior sigmas. They seems to reduce the sigma as the number of experiments grow in some way using some heuristic. Yes. Yes, they are, but they also, what they actually do, and I haven't really mentioned here, is they have a weight to each experiment. So old experiments get a lower weight. So like the last 20 get weight 1.0. Then they have a linear decay of the rest of the weights. So they actually take the sigmas of the past have a lower weight than the sigmas of the future, so to speak. So yes and no. They have these weights both for finding the new mu's or the means, but also for finding the new sigmas. They're using this kind of weighting heuristic to weigh the experiments in a bit different way. Yep. Yes. No, actually no. No. Actually not. No, that's one weakness of this TPE algorithm. It actually doesn't model interactions between parameters. There's been a number of talks about this and how they could do that, but that's certainly one of the bigger weaknesses of this algorithm. So, good question, and unfortunately the answer is no. Okay, so the next step. Now we basically have these Gaussian or mixture models for each of the two groups. And here you can see, I guess this can be the top group and this could be the rest group. And this is some kind of single hyperparameter. And each of these lines is basically the random sample you drew from the top group. So you got a sample here, here, and you can see it's high probability to be in the mode, so to speak, of the distribution. And now you want to rank them. So should you simply select this one because that is at the mode, the highest value for that top distribution? Well, no, that's not how they do it. So they instead take this ratio that I spoke of. So they basically divide the likelihood of being in a top group with the likelihood of being in the bottom group. And that division basically becomes this value. So if you take this point and you divide that value with that value, you get a rather high value here. And if you take this point, you get this ratio. And in this way, you can rank them and you come to the conclusion that the best point to choose is this one, in this case. Cool. Okay, so I'm almost finished now. I'm probably over time, or a bit. So I also mentioned the early stopping issue, and I think that's we quickly realized if you don't have an early stopping mechanism, it will not really work in a good way. So running every experiment for like 200 epochs will take far too long time, so you want to speed up the whole study as much as you can. And for some experiments like this one, it can be quickly realized by just looking at each epoch here that this won't lead to any major improvements. So you can stop this rather easily. So this is basically looking at each of the point, and they're using, if you can't improve basically the metric for the last 10 epochs, you first do a learning rate reduction and you try once more. And if it can't in a second run either find an improvement in 10 epochs in a sequence, you halt the whole experiment. So that's the simple heuristic used right now to just, at some point stop each experiment. And that can lead to significant improvements in speed and still allow some experiments like this one, which really took a long time to come to the optimal level. Yeah, here are some published results about how well TPE works compared to random search. And yeah, what you see here is it's really hard for random search to, in this case, get below this 0.22 number, but very early on the TPE can come down to a much improved metric and actually stay down there very much quicker than the random search can. But notice the number of trials, like 200 experiments already here. But if you didn't have TPE, probably you can stop with TPE in this case for like 300 experiments. If you had random search, well, you wouldn't even be able to stop here after 1,000 experiments. Yes. No. And I was trying to ask that question, but it was so many people asking them, so we didn't have time to get that in. But I think it's really surprising that they don't include this one in the 8 selected algorithms they do have. Surprising, and I don't know why. I wish I could get that answer from them. Cool. Okay, this is basically the final slide. And you know, the first conclusion that you make for having experiment with this is, of course, always tune your hyperparameters. That's like, you wouldn't build a model without doing this after you started making use of a technique like this. But there are a number of problems as well. For one, in Hyperopt, the code is really hard to follow. Not only that, but it's also written in a rather abstract way, so you can't really debug it in a normal way, and the code and variable names is given really weird names, so it's hard to really follow in a good way. It's also, you know, the question of how to do early stopping. It works rather okay with a simple heuristic used now, but I think we could significantly improve that as well. And surprisingly, you know, once you run a whole study, you would like to just see the distribution of each parameter to see, okay, this is how certain I am, and the range you should really work with. But it's actually kind of hard to get that out of Hyperopt. And I think that's the first thing you want to have when doing this, and it's surprisingly hard. And this is the transfer learning aspect I mentioned that Google has spent a lot of time with in trying to use previous studies, extract some insights from them, and feed them in as a starting point, so you don't have to start from scratch for every new study that you run. It's also hard, you know, something I spend a lot of time with is how to handle exceptions, like we actually saw in the beginning here. If you, for example, have an out-of-memory problem because the model and the batch size is too big, the model will actually search still for that, so it will basically try to move the parameter values in a direction that will cause it to always get out of memory. And you would like to inform that somehow in a good way to the algorithm saying you shouldn't move past this point because it will always fail. But it can't be done today in a good way. And parameter interactions, as we mentioned, that's not really handled either right now in a good way. So if weight decay combined with batch size or with a number of layers or hidden units, perhaps if you look at the combination of the two together, we can even faster come up with the best values. And that's not being handled today. And Hyperopt doesn't support these batched Gaussian processes that Google is using either. And as just a final point in this is some, I got a good question before I started, and you know, they talk about this black box optimization as a good thing, saying it can work with any model, so it's model agnostic, which of course is good as well. But it's kind of weird to use a single scalar metric like the test metric as the only guidance to this learning algorithm, to this optimization algorithm. We have so much more. We have the whole model. We have gradients. We have so much more information we could potentially make use of to try to get some more insights how well the model is performing. Can you really just put that into a single, you know, test metrics? I think you can do much better. And if you attended this other meetup before, talking about the model introspection, how you can actually try to explain predictions, you see this gradient-based method seems really promising. And I think that can be fed back into also these kind of parameter tuning algorithms, and that would make it even faster to find the best values to have. But that would not make the black box optimization anymore. Then it would be dependent on models that actually have gradients in them. But still, that would make it learn much faster, I think.
And that's basically what's happening when you're using Adam or something, right? As an optimizer.
Yeah, exactly.
Extra parameters.
Yeah, a parameter So it has a learning rate for every parameter in the model. And exactly. Cool. Okay, that's all from me. Thank you for your attention.
I think we have time for some questions, but just 5 minutes maybe.
Yep.
Then we'll have short break.
Yeah, I'm going to try to see how the experiment we started actually worked out, but feel free to, yeah, please go ahead.
So, say you only have like one or a couple of GPUs. Is there any simple things you can do?
Well, even with one GPU, you're heavily helped with having an automated hyperparameter tuning. It's just it will have to run one at a time. And so it doesn't really matter. It's just, the number of GPUs or machines you have just speed up the process. But if you don't do anything, even if you just have one GPU, then you're back to either doing grid search or hand tuning, which is super hard to do. So yeah, I would. I'm sure there are some person in the world that can guide you into whatever data or model you have. They can say these are the hyperparameter values, but I've never spoken or seen such a person yet. The thing is, every model calls different values for the hyperparameters, but not only that, but the data and how that looks also affects how the hyperparameter should be. So I think it's super hard. Yeah, Sorry. Sorry. Yeah. 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 I'm not sure I follow you actually. What would you want to actually do?
Because if you want, so say you have some convolution.
Yeah.
And you have a dense layer at the end.
Yeah.
And now you're considering changing the size of it.
Yeah.
You could potentially use the previous layer.
Yeah. But remember that this one is not looking anything in. Okay. Yeah. Yeah. Okay. So one way to rephrase your question a bit is, can you use some insights from previous experiments in how to change the model, add layers, or even perhaps initialize some of the layers in the model? But for these algorithms, at least, they are black box optimization. So they don't look anything into the model or don't have any of that information in their current implementation. I think with more gradient-based tuning algorithms, it could start to be possible. But this is more into model introspection, I think, than these kind of hyperparameter tuning areas. So that would mean more trying to understand, how the activation distributions of the previous layers look like to guide you into how to design the others. And that is a rather different thing than trying to just optimize the hyperparameters, I would say. But, okay.
Would it be possible to treat this as a reinforcement learning?
Yeah, good question. This is, of course, not a problem you can differentiate. So you can't get any gradients direct, for each of the experiments. It's just inside the model you have gradients. So reinforcement learning is usually the go-to guide, so to speak, for these kind of problems when you don't have any gradients. And I would think so, but I have not seen anyone try that. It seems like a reasonable thing to do because you get some kind of reward for each experiment. And if you just can phrase your parameters as this kind of policy network as reinforcement have, then it should in theory be possible. But since you perhaps don't have these kind of state actions as most reinforcement do, which is a set of actions you do after each other, this is like, okay, you set a set of values to begin with and then you go for it. You don't take actions while running an experiment. So you only have like one action to take. So that could be one reason, perhaps, just thinking clearly about it. But yeah, good thinking. Yes. Okay, yeah. Forgot.
Now, with the system that you showed now,
Yeah.
how much of it is Hyperopt and how much is sort of what you built and what you built with the open source?
I say 95% is. Oh, okay. I should repeat the question. How much is of the system we have now is based on the open source version? How much is added by our code that we have? And 95%, I would say, is still the open source version. It doesn't have some of the, you can add limitations to avoid this kind of GPU out of memory issues. You can do the early stopping. That is not included in Hyperopt. And just to be able to integrate it quickly into the existing like platform or libraries we have, that's a lot of code, more like plumbing code. But I think anyone that has some kind of libraries they use or reuse between projects, they need to do this integration of the Hyperopt system. But still, the main functionality is in Hyperopt, so you can quickly get up to speed to something similar like this if you start with Hyperopt, I would say.
Thank you for a very nice presentation.
Thank you.
It's very exciting with someone like being skeptical about the popular Google paper that they have.
Yeah.